All right, so we're going to start today as a continuation of yesterday. So yesterday we talked about stoichiometry. We talked about how we can use balanced chemical equations and molar masses and some other information to determine problems and to determine things like how much product should I expect, what kind of yield should I expect, how much reactant am I going to use. So all of those things come into handy here. And what we're going to move on to now is kind of the last dimension of that. And that is this concept of completion. And so I'm going to start by posing a question to you. Do all reactions go to completion? And as we're thinking about the answer to that question, let's consider a simple example. If I have carbon, charcoal, and I'm burning it in oxygen, I will get carbon dioxide. And so there's two things I want you to think about. Is it possible that if I were to light a charcoal brick outside or in your room or wherever, that all of the charcoal would burn up? Is it also possible that if I were to take that same piece of charcoal, light it on fire, and then put it into a some sort of closed container, would all the charcoal burn there? So what I want you to do, take a couple of minutes, talk to each other. I'm going to mute myself while you talk. And I want you to think about this kind of the fundamental question here. Do all reactions go to completion? And if they don't go to completion, then what can we do? How can we recognize when a reaction has not gone to completion? So go ahead and take a few minutes. Again, I'm going to mute myself here and let you talk.
I feel like it does go to completion, but I think it does take it to different stages though. It doesn't just go to immediately burning away.
Under which condition, the container or the bedroom situation?
Both.
I think the charcoal would burn completely if it was in a jar. And then if you lit it up in a room, I don't think all of the charcoal would burn, because if you like start a bonfire, not all of the wood is going to be burned exactly.
If it's in a closed jar, though, it'll eventually run out of oxygen, so it won't burn completely.
But all of the fire and whatnot would be trapped, so there wouldn't be any place for it to go, right?
Well, it'll eventually stop burning in the jar. It'll run out of oxygen. It has to have the oxygen. Like, have you ever had a candle and put the lid on top of it? Yeah. The flame goes out. I'm assuming that's probably what's going to happen with the charcoal. But I think it would completely burn in the bedroom or in the room.
All right, so we're making some pretty good points here. We're making some pretty good points overall. To Brett's original point, there is the factor of the oxygen. We do have to consider the presence of oxygen. And if the oxygen runs out before the carbon burns, then the carbon's not going to completely burn. Now, to Malaz's point about the bonfire, you're right. What happens in that circumstance is kind of the same, though, where the carbon that is in the wood is seeking to combust, but there just isn't enough oxygen around for all of the wood that you need to burn in a bonfire. And so what happens is you get charring, you get ash, you get unburned pieces of wood, unless you start to spread that wood out so that it has a greater surface area and access to oxygen. But you don't want to do that in a bonfire, because the whole point of a bonfire is that it's in one space and everybody can get around it and still be somewhat close to each other. If you spread it all out to take up half of your field or your backyard, then you're gonna have other issues to worry about there as well. So bottom line, do all reactions go to completion?
No.
Can they? Is it possible for any reaction to go to completion?
Yeah, they can, but not all.
Okay. So what is necessary if I'm going to have a reaction completely react and have no reactants left over? Let's say I've got the carbon and I've got the oxygen. How can I ensure that there will be no carbon left over and no oxygen left over when the reaction is done?
Are you talking like you need 2 parts oxygen and 1 part carbon to completely balance each other out?
In a sense, yes. So this is where your stoichiometry would come in. Let's say that I take my charcoal and I weigh it out and I've got 5 grams of it. I could use my stoichiometry to figure out how much oxygen I would need, and then combining those exact amounts together, theoretically, if I got 100% yield, all of the carbon would burn up, all of the oxygen would get used, and it would all get converted to carbon dioxide. That's where the stoichiometry comes in. That's why we do stoichiometry for those kinds of scenarios, where I know I have this much of one reactant and I need to figure out how much of another reactant to add to get it to react completely. Now, if it's really of interest to us to get all of the carbon to burn, what we will often do in many cases is add excesses of oxygen. This is what happens in your car. When you burn gasoline in your engine or diesel fuel, depending upon what kind of engine you have, your car doesn't just let in the exact amount of air, it overcharges it. It puts more air into it so that there's plenty of oxygen available and we get that complete combustion, or at least as near as we can get to complete combustion inside of that engine, so that the engine works the most efficiently and doesn't leave behind all these black deposits from the unburned gasoline vapor. And if you have, that's the primary job of the carburetor in the car. And if you've got a supercharger or turbo on it, that puts even more air into it to try to get it to burn even more cleanly, more quickly, more precisely, which is exactly what you need for that higher octane engine. So what we're getting to in all of this is the idea that when we set up chemical reactions, sometimes there is going to be occasions where we run out of something. And that phenomenon is known as the limiting reactant. So in a case where we have reaction taking place and one of the reactants runs out and another one or one stay behind, we call the one that runs out the limiting reactant, because when that substance runs out, the reaction is no longer able to continue. If I put that flaming charcoal into a glass jar and seal the jar, eventually I'm going to run out of oxygen in that jar. And when I do, the fire is going to go out. And with it will be left behind a whole bunch of carbon, presumably. Brett made the example of lighting a candle and then covering it with the top. Candles burn by the vaporization of paraffin wax. The paraffin wax vaporizes, mixes with oxygen, and burns. And that's what we see happening at the wick. And if we close off the paraffin and close its ability to get new oxygen, eventually the paraffin's not going to have any oxygen to burn on. And so what's the first thing we see? We see that the flame that is on that paraffin candle will start to get darker, black, sootier, because the carbon in the paraffin will start to take some shortcuts from a combustion standpoint and leave behind soot instead of carbon dioxide. And then eventually just reaction stops and the candle is out. So the limiting reactant is the substance in our reaction that runs out first and therefore dictates how much product we can make. All of the other reactants, whether it's just one reactant like oxygen or carbon, or multiple reactants, say we have a reaction that requires 3 different things to react, those would be excess reactants. And then a stoichiometric amount is what we talked about before. Let's say that I weigh out my carbon and I say, okay, 5 grams of carbon requires this much oxygen. I'm going to weigh out that much oxygen exactly. That's a stoichiometric amount. And assuming 100% yield, those 2 things react and they completely turn into products and there are no reactants left over. But before we get into the calculations here, limiting reactants can be a little bit bendy in terms of trying to figure out a good way of representing them and thinking about them. So I want to bring you an alternative kind of analogy here. Let's say that a fast food establishment like Wendy's is selling cheeseburgers. I know, imagine that. Now, let's say that for the sake of argument and for the purposes of this exercise, a cheeseburger at Wendy's has a particular recipe that they cannot deviate from. Have it your way doesn't mean a lick of difference at this particular Wendy's. And so their version of a cheeseburger being mass produced in the back of that store has 1 bun, a single quarter-pound patty, a slice of cheese, 2 pickles, and 3 onions. That's their recipe for a cheeseburger, and by God, they're not going to deviate from it. Now, in this same analogy, keeping this in mind, and just as a matter of clarification, because every time I do this particular exercise, people get a little bit confused. The numbers boxed in orange are values in terms of how many of each item is involved in the cheeseburger. The values in black are the actual ingredients. And the reason I mention this is it's often confused that when we get to the next slide, someone inevitably will say, well, I thought you said it was a 1 1/4 pound patty. So just keep that in mind. For the cheeseburger, it's a 1/4 pound patty. Now, again, I'm going to lay out here and let you talk. What I want you to do is this. If this is my ingredients list, And this down here is my inventory. How many cheeseburgers am I able to make with this recipe and this inventory? Once again, I'm going to lay out and let you talk. Go ahead and try to come up with a response.
I'm
The-
pretty sure it'd be 13. I think.
10. They'd run out of
Oh, hamburger meat, right?
no 3 onions, so they would, yeah, they'd only be able to make 10. Yeah, the onions would run out first.
All right, so walk us through the process, Brett. How did you come up with the 10? How did you come up with onions?
So it's 3 onions per burger, and we have 30 onions in stock. I mean, 30 divided by 3 is going to give you 10. And I think somebody said 5 pounds, but you can make 20 burgers with 5 pounds. Yeah, and then the rest are, 50, yeah, you can make 50 burgers with 100 pickles.
Okay, so yeah, this is pretty much the process that you'd want to do. Starting with each one of the ingredients, you would look at it and say, okay, how many products, how many burgers can I get out of each one of these ingredients? And then you do that and say, okay, 13 for the buns, 20 for the meat, 25 for the cheese, 50 for the pickles, and 10 for the onions. And then ultimately you would select the answer would be the one that gives you the least product, because that is ultimately going to be your limiting reactant, and your yield would be 10 burgers, which means that all of the rest of these would be excess reagents, excess reactants. And could you make some delicious burgers with the remaining ingredients? Well, yeah, you can make 3 burgers after everything was gone with just meat, cheese, and pickles. And I'm sure that'd make somebody happy. But it wouldn't satisfy the conditions for the burger here. Okay? And so this just kind of summarizes all of that. Now, how do we apply this idea that we just saw in the cheeseburger analogy to something that's a little bit more chemistry oriented? Well, the way to do it is if we compare how much reactant number 1 makes in terms of product and how much reactant number 2 makes in terms of product, and we compare them against each other. So long as we're comparing the same thing, and this is an important distinction to make, so long as we are comparing the same thing, we can do exactly what we just did. The one that makes the less product is the limiting reactant, and the lesser product is the theoretical yield. And so that's how we approach these kinds of problems, where it isn't glaringly apparent to us what our limiting reactant is. Now, in the cases of some of the ones that we did yesterday, we had nitrogen reacting with hydrogen, and we were told that nitrogen was in excess. And so what we do, we ignored the nitrogen and we focused just on the hydrogen and how much ammonia the hydrogen could make. That was the kind of thing. So if we're told that something is in excess, then we know that the limiting reactant is the other thing. But if we're not told something is in excess, if we're told I've got 30 grams of this stuff and 80 grams of this stuff, the only way I can determine whether the 30 grams or the 80 grams is the limiting reactant is to see how much product they make. And the thing that I caution every one of you on is that it's very easy to turn around and say, okay, well, I've got 30 grams versus 80 grams. Well, that's easy. The 30 grams is going to be the limiting reactant. There's so much less of it. The problem with that line of thinking is that you're not taking into consideration molar mass. What if the thing that is 30 grams is hydrogen and it has a molar mass of 2.02, and so we're dealing with 15 moles of the stuff compared to half of a mole of the thing that's 80 grams, but much more massive, bigger molecule. And the other thing that we're not considering is stoichiometry in terms of the balanced chemical equation. If the thing that is 30 grams reacts in a 1-to-1 ratio, whereas the thing that is 80 grams reacts in a 1-to-6 ratio, it might get used up way more quickly than the other stuff is. So we've got to do our work. We've got to do our calculations to actually figure this out. We can't just assume that the smaller one is going to be the limiting reactant. So let's do some examples here. Coming back to this idea of charcoal, I've got a 31.5 gram brick of charcoal. It's burned in an atmosphere of 102 grams of oxygen. We want to know how much carbon dioxide is going to be made. So to do this, we need our balanced chemical equation. And we need our amounts of each one of these. So we're going to need a little bit more space than what I have here. So I'm actually going to switch over to the whiteboard. And if you didn't copy everything down, that's okay. We're gonna recreate it on the whiteboard here. So we have carbon plus oxygen making carbon dioxide. We've got 31.5 grams of carbon reacting with 102 grams of oxygen. And the question is, how much carbon dioxide are we going to make? Now, to answer this, we're going to follow the exact same procedure that we did in the cheeseburger example. We're going to take our 31.5 grams of carbon and we're going to convert it into carbon dioxide. And we're going to do the same thing with our 102 grams of oxygen by taking it and converting it to carbon dioxide also. Now, it's important that in these calculations that we are doing, that we end at the exact same place. So it's not just good enough that we end up at carbon dioxide. We have to have the same unit for carbon dioxide as well. So since we're ultimately going to go to grams anyway, we're going to make both of these into grams of carbon dioxide. If I didn't do this, if I turned this into grams of carbon dioxide, but this to moles of carbon dioxide, I wouldn't be comparing the same thing, and I'd end up in the wrong place. Similarly, if I went and turned this into grams of oxygen and compared it to the grams of carbon dioxide created by the oxygen, that wouldn't be the same thing either. Grams of oxygen and grams of carbon dioxide are not the same thing. I wouldn't be able to make the same kinds of comparisons. So ultimately, what I have to do is that direct comparison between the two. So let's start with our grams of carbon. And we know that our first step, if we follow our mole map, is going to be to convert those grams of carbon into moles of carbon. The ratio we get from our periodic table, 1 mole of carbon is 12.01. Grams of carbon. My grams of carbon cancel. My second step is to turn the moles of carbon into carbon dioxide. I get that from the balanced chemical equation. Luckily, my balanced chemical equation shows that everything is 1 to 1 to 1. So 1 mole of carbon is equal to 1 mole of carbon dioxide. My moles of carbon cancel. My last step is to turn the moles of carbon dioxide into grams. So I need moles of carbon dioxide in the denominator, grams of carbon dioxide in the numerator. 1 mole of carbon dioxide. Molar mass of carbon is 12.01 plus 16 times 2 for 44.01. And so if I do out the calculations here, I get 31.5 multiplied by 44.01 divided by 12.01 to 3 significant figures. I get 115 grams of carbon dioxide. Now, if this was the only piece of information I was given, if I did not have this last piece right there, then I would be done. I would say, okay, the yield here is 115 grams. But since I don't know that, since I have that other piece of information right here, but since I have this, I got to do the next step. I got to compare it to how much I'd have gotten from the oxygen. And so I have 102 grams of oxygen, and I'm going to need to convert that So grams of oxygen in the denominator, moles of oxygen in the numerator. 1 mole of oxygen, 2 times 16 is 32. So my grams of oxygen cancel. I now need to take my moles of oxygen and turn it into moles of carbon dioxide. And so one of the wonderful things about the limiting reactant problem is that a number of the things that we do end up being somewhat redundant. So my mole-to-mole ratio, obviously the dioxide is going to be the same. In this case, the oxygen is the same as well. And then the last step, where I convert the moles of carbon dioxide into grams of carbon dioxide, well, what do you know? That's the same as well. And so 102 times 44.01 divided by 32 will give me 140 grams of carbon dioxide. And so what can we say about this? Well, we can say that this is our theoretical yield. 115 grams of carbon dioxide is our theoretical yield. Carbon is the limiting reactant. Oxygen is in excess. (115 grams of carbon dioxide is the theoretical yield. So we can say all of these things based off of these calculations. Now, the only other thing that we could possibly say is if we wanted to know how much excess reactant is left over. Well, there's a number of different ways to approach this problem. You can take it a number of different directions. One way is you start with the limiting reactant, 31.5 grams of carbon. You convert it to the excess reactant, the oxygen. And you just subtract that amount from the excess that you started with. So let's say I do this calculation. It tells me that I would have used 80 grams of oxygen, and so I subtract 102 minus 80, and I get 22 grams of oxygen left over. The other method is I take my two yields, I subtract them from each other, and then whatever that difference is, that's the excess yield. And I just convert that back to excess reactant. In my mind, that's actually easier to do. Either way works. You'll get the same answer, or at least roughly the same answer. but this one kind of takes advantage of a lot of the work that you already did. So just as a illustration, I'm going to show you this this second method. So we start 140 grams of CO2 minus 115 grams of CO2 would give me 25 grams of CO2. And so it's this 25 grams of CO2 that I'm ultimately going to be working with. And what I'm going to do is I'm going to go back from CO2 to grams of oxygen. So luckily, all of the legwork has been done for us already in this conversion. Basically, I'm just going to take this conversion and flip it around, reverse it. So 44.01 grams of CO2 in 1 mole of CO2. One mole of CO2 is equal to 1 mole of O2. And then finally, 1 mole of O2 is equal to 32.00 grams of O2. And if I do this calculation, 25 times 32 divided by 44.01 to 2 significant figures would give me 18 grams of O2 left over. Now, like I said, you could have run this back and done it the opposite way. 31.5 grams of carbon, and if we had done it that way, let's just take this out here. .31.5 grams of carbon, and then following the map here along, 12.01 grams of carbon in 1 mole of carbon, 1 mole of carbon in 1 mole of oxygen, 1 mole of oxygen in 32 grams of oxygen. If you had done that calculation, 31.5 times 32 divided by 12.01 would give you 83.9 grams of oxygen used, 102 grams of oxygen minus 83.9 grams of oxygen used would give you 18 grams of oxygen left over. So you could have done it either way. Like I said, both processes involve a stoichiometry and a subtraction. It's just a matter of which order you do them and what you start with. Idea is the same either way. Any questions about this particular example? or about the side street we just went down with regards to excess reactants?
No.
All right, then let's get back. And I'm going to let you do one now. So we've got acetylene. Acetylene is used by welders in torches to make welds at temperatures up to 3,500 degrees Celsius. If 52 grams of acetylene and 188 grams of oxygen combine, according to this unbalanced reaction, which is the limiting reactant, how much carbon dioxide do we get? Now, just to get the ball rolling a little bit here, let's go ahead and balance this together and make sure that we're on the right page. And so we've got the thing balanced now. Just a little trick that can help to balance that quickly. When we have combustion reactions like this, a real key to knowing whether or not you're going to need to double it or not comes in what you do with the hydrogens. If to balance out the hydrogens, you end up with an odd number in that spot, you know that you're going to have an odd number of oxygens on this side, which means you're going to have to double everything so that you can get it to even up here at the end. So that's how I knew to start with a 2 here as opposed to just a 1, because with 2 hydrogens here and 2 hydrogens here, that meant that I was going to have an odd number of oxygens. At any rate, go ahead and try to solve this one on your own, and we'll come back in a few minutes and talk about it. All right, so if you're still working, go ahead and keep going. We'll get kind of the process started, and you can kind of check yourself and your progress. So the thing that we're doing here is, since we're trying to figure out how much carbon dioxide is generated, we should use that as our ending point. So in the end, we are going to figure out the number of grams of carbon dioxide for each one of these. Now, the process to get there, again, relatively similar, but different starting points. So the first thing we need is the molar mass of acetylene. Molar mass of acetylene, 12.01 for the carbon times 2, 1.01 for the hydrogen times 2, 26.04 grams is the molar mass. So 26.04 grams of acetylene in every mole of acetylene. Now we want to use our balanced chemical equation. Two moles of acetylene is equivalent to 4 moles of carbon dioxide. And as we saw before, 1 mole of carbon dioxide weighs 44.01 grams. Now, if you're not sure where we got that, that's been the molar mass we've been using for carbon dioxide in pretty much every other calculation that we've done thus far. And so if I carry all of that through, 52 times 4 times 44.01 divided by 26.04 divided by 2 to 3 significant figures would give us a yield of 176 grams of carbon dioxide. So that's part one. We have no idea whether or not 176 is a high number, a low number, or the right number.
Okay, I got this. I'm sorry to interrupt you. I got the same answer. I'd have already been say something. I had got the same answer, but I did not get it how you got it.
Okay.
So I was trying to see how you went on ahead and wrote yours out before I said something. So I did come up with 176.
Okay.
So what happened was I did the 52.0 C2H2 times 1 mole C2H2 over 5208, but I wasn't for sure if I needed to go ahead and put, I don't know. I know that it's like 4, the carbon is 4, the hydrogen is 4. So I didn't know if it was supposed to be 2 moles per whatever or what, but like I put 1 mole is 5208. And then the second one, I said times 1 mole of CO2 over 1 mole of C2H2.
Okay, so I'll tell you what, you kind of lucked into the right answer. Because basically what you did, for whatever reason, you doubled the molar mass down here and then did not double the mole-to-mole ratio. So you didn't double when you're supposed to here, and you doubled down here when you weren't supposed to. So the mistakes kind of negated each other. And you kind of got lucky.
Because after that, I put times 176.044 grams of CO2 over 1 mole of CO2. And then I did the multiplication and division. So
Okay. So I see what you're doing. The problem with what you're doing is the only time we need to apply these numbers in the balanced chemical equation is in this middle step right here. So these numbers, the 2, the 5, the 4, the 2, only get applied in this step right here.
Okay.
Everything else is just a molar mass, 1 mole of the substance for whatever the sum of the masses on the periodic table is. To do what you were doing, you would have needed to, instead of, you said 176 here for carbon dioxide.
Because you needed to find the mole. Yeah.
You would have had to put a 4 down here.
I knew that. And that's what I wasn't, because looking at it, when you balance something, I felt like to get the answer, they want like, well, you got 2 of these now. So you need to, I just felt like, okay, never mind. Okay. Well, I'll just go ahead and
this step and this step require molar masses. Molar masses, by definition, are for 1 mole of the substance.
Yeah. So I felt like I was supposed to put 2 over 5208.
No, if you do that, that's fine. But it's an extra step that you don't need to do.
Okay.
You can just do 1 C2H2 and 1 CO2.
Okay.
The numbers that you're talking about come from the balanced chemical equation, and they are only addressed in this step right here.
Okay.
So when we do the mole-to-mole conversion, when we're converting from one substance to another, that's when we pay attention to the coefficients.
Okay.
That's when we start putting those numbers in. Otherwise, we don't need to even worry about them. That could, the number could be 30 for all we care. We're still only going to calculate the mass of 1 mole.
Okay.
Okay. So, yeah, you end up coming to the right answer. You just took what I would call the extremely long road to get there.
Okay.
So, watch out for that. Watch out for that when you're addressing these kinds of things. Make sure that when it is when we're doing these kinds of calculations, we don't have to overcomplicate them.
Okay, because you did account for it, because I felt like you need to account for it. So you accounted for it when you put 4 over 2. That's
Yeah,
fine.
this is
'Cause
where
I
you
wanna-
account for it.
Okay. Yeah, that's fine. I understand.
Okay, so based on the acetylene, we expect 176 grams of carbon dioxide. Let's do it out for the oxygen and see if we end up in the right or in the same spot or a different spot, and take it from there. So 32 grams of oxygen in a mole. This time we've got 5 moles of oxygen for every 4 moles of carbon dioxide. And 1 mole of carbon dioxide is still 44.01 grams. So if I do that calculation, 188 times 4 times 44.01 divided by 32 divided by 5 to 3 significant figures again, I end up with 207 grams of carbon dioxide. So again, we choose the lower of the two, 176. That becomes our limiting reactant and our theoretical yield. So limiting reactant is acetylene. Oxygen is in excess. 176 grams of carbon dioxide equals the theoretical yield. Again, as we talked about yesterday, we can use that theoretical yield and compare to, let's say that we did do this reaction in the lab and it generated 159 grams of carbon dioxide. We could compare those two and get a percent yield, get an idea of how efficiently the reaction ran. Any questions about this example now?
No.
Well, congratulations. You've made it now to the end of chapter 7. And so why don't we take a 10-minute break? And at the end of that break, we'll actually start jumping into chapter 8 a little bit, and start talking about solutions and reactions that occur in solution. So 10 minutes, let's come back at 10:15, and we will resume by going into the next topic. Go ahead and take a break here. So in chapter 8, we're talking about aqueous solutions, and we're getting into aqueous solutions not necessarily for the first time. We've talked a lot about things that are dissolved in water and the solutions that form when water dissolves things. We haven't really talked a whole lot about the chemistry of those objects, though, and so that's really what this chapter is all about. And so we're going to start off today with kind of just a fundamental concept, a way of looking at solutions in water and breaking them into categories and starting to discuss some of the key attributes that some of these solutions have. And so just as a review, an aqueous solution is any solution that water is the solvent for. And we can break these into categories based upon what happens with the solution once the solute has dissolved. And we can break the two categories as electrolytes and non-electrolytes. Now, electrolytes are solutions that conduct electricity. So if I put up the solution to a conductivity meter or an open circuit of some kind, the solution would complete the circuit and conduct electricity. And there are certain types of solutions that are capable of doing this. And we'll get into more of that in just a minute. The other type of solution is the non-electrolyte solution. And the non-electrolyte solution does not conduct electricity at all. And so from that standpoint, we've got some pretty stark differences between the two just on that concept alone. Let's talk a little bit about electrolytes though. As I said just 30 seconds ago, electrolytes are solutions that are capable of conducting electricity. Now, what does that mean? Well, that means that in order to conduct electricity, we have to have a way for electrons to move. We have to have an ability to stabilize those electrons as they're moving. And so electrolytes have ions in the solution that are capable of stabilizing those electrons and allowing them to flow through the solution. And so as a result, there are 3 different types of solutions that can form and make electrolytes. There are solutions of ionic compounds, that is salts. There are solutions of acids, and there are solutions of bases. Those are the 3 types of compounds that are capable of making electrolytes when they dissolve in water. Now, of these 3, we are probably the most commonly familiar with the ionic compounds, the salts. In fact, when we think of electrolytes, thanks to marketing and just kind of a general misunderstanding of the field, most of the time we think of electrolytes, we think of things like Gatorade or sports drinks, those kinds of things, because at their very heart, what you've got in Gatorade is a whole bunch of water that has had some salt mixed into it to help you replace your electrolytes that you would lose through sweating, through exercise, or some other kinds of strenuous activity. But that's not all we can do. We can actually classify electrolytes into 2 categories of their own. There are the strong electrolytes. These are the things that really do conduct electricity quite well. And then there are the weak electrolytes, things that do not do as good of a job of conducting electricity. They do so rather poorly. The difference between them is in the quantity of ions that are produced by them when they dissolve in water. So strong electrolytes are characterized by having complete dissociation. That is, all of the molecules that make up those electrolytes, those substances, whether they're ionic compounds, acids, bases, when we get them into water, water splits them up completely, and I've got lots of those little ions in that solution, and lots of ions means lots of conductivity and really good electrolytic power. So we can see here in the example, sodium chloride. I take sodium chloride, which is this massive array of positive sodium ions and negative chloride ions, and I put it into water. The water splits apart all of those sodium ions and those chloride ions from each other. They're all now floating around in this water, and since they're all charged up because they're ions, they're very capable of conducting electricity and conducting it quite well. And since I have so many of them, they do a good job of that. Weak electrolytes, on the other hand, we see this partial dissociation. So I take a weak electrolyte, I've got it, and I put it into water. And what happens is when I dissolve it into water, the water surrounds it. We get that sphere of hydration. And for the most part, that's all we get. The bonds in this molecule are strong enough and are not stabilized enough by the water that they stay molecular more often than not. Now, that's not to say that they always stay molecular. Again, we're talking about a weak electrolyte. There's partial dissociation here. What happens is some of the ion or some of the molecules will come apart. And when they do come apart, they will form ions. But this circumstance of dissociation is far less common than the first circumstance where they were all together. In fact, this dissociation happens depending upon the strength of the ion, the the dissociation strength, you're talking anywhere between 1 and 10% dissociation. So think about that. Every 100 molecules that go into water, either, somewhere between 1 and 10 of them will actually break apart and form ions. So we still have ions in the solution, but the number of ions is far, far less. And as a result, the electric charge is far less stabilized. And we do see conduction of electricity, but not to the same degree at all. And that's an important thing to note. But we do not see nearly as much dissociation. We do not see nearly as much electricity conductivity. And that shows if we actually try to measure the conductivity of acetic acid compared to sodium chloride, which you will get in a video form later this week in lab, the comparison between these two is very, very stark in terms of the amount of electricity that they are able to conduct. So how do I know what kinds of materials to put in this first category of strong electrolytes and what kinds of materials go into the second category as weak electrolytes? Well, the good news is the characteristics are very, very easy to find. Ionic compounds, for example. Ionic compounds are always going to dissociate. So if it dissolves in water, it dissociates into ions if it's an ionic compound. If it's a base, and it's a strong bases will dissociate completely. They will make strong electrolytes. Same thing with strong acids. If they dissolve, they dissociate, and they do so in a very strong way. Really, the only things that come off as weak electrolytes are our weak acids and our weak bases. And that's because in weak acids and weak bases, we usually have other effects that are coming into play. We're usually looking at covalent compounds, and the covalent compounds that we're looking at tend to be pretty set in their covalent ways. Their polarity is not terribly great. They don't dissociate very well with each other because the covalent bonds are there, and they're not stabilized as well with the water as the ions are in ionic compounds, so they tend to stay molecularized. So that's really what's going on in terms of those things. Now, the last category, the one we haven't really talked about yet, these are the non-electrolytes. And in non-electrolytes, we have no ionization occurring, none whatsoever. And so as a result of that, we don't get any conductivity either. And so one place where we can see that is in pure salts. So ionic compounds where we do not have aqueous solution. If I try to hook that up to electricity, the charge has nowhere to go because the ions here are fixed in place. And so there's nothing there to stabilize the charge. And as a result, the charge doesn't go anywhere. Similarly, if I have molecular substances like ethanol, sugar, ethylene glycol, and I put them into water, I would see a similar kind of result. These substances, their covalent tendencies are so strong that they don't dissociate at all. They're non-acidic, they're not basic, and they're certainly not ionic. And so molecular compounds that don't have acid-base properties to them are going to be non-electrolytic, even when dissolved in water, as is the case with the ethanol in water here in this panel. So those are our general ideas as far as electrolytic behavior is concerned. Let's move on now to talking about solubility. And when it comes to solubility, we have to understand that while ionic compounds are electrolytic if they do dissolve in water, not every ionic compound does dissolve in water. But luckily for us, there are some guidelines that we can follow that'll help us to figure out whether or not an ionic compound is something that is going to dissolve in water and therefore be electrolytic, or stay out of water, to not dissolve in the water, and therefore be non-electrolytic as a result. Now, the thing I want you to think about as I start to present these solubility rules is that there is a hierarchy here. The first solubility rule that I'm going to show you supersedes all of the other solubility rules that follow it. And the second one that I'm going to show you will supersede the third one I'm going to show you, and so on. So when I flip this over and start going through the solubility rules, I want you to keep that in mind, that if something is on this first list, this is the list of things that are always soluble in water. So if I see a compound that has one of these in its compound, I know it's soluble. Even if the other ion in there is usually insoluble, if it's paired up with one of these, it's going to dissolve. It's as simple as that. So the things that are soluble, on this list we have nitrates, NO3- ion. We have acetates, CH2H3O2-, or in its structural form, CH3COO-. Any of the alkali metal ions, so we're talking lithium, potassium, sodium, rubidium. Any group 1 ion is going to dissolve in water. Anything with the ammonium ion in it is going to dissolve in water. Anything that has a chlorate or perchlorate ion on it is going to dissolve in water. So this is my list of soluble ions. Now, most of these are anions, but these are my soluble ions. And so any compound, any ionic compound that has one of these ions on it is going to dissolve in water and is going to yield a strong electrolyte. What I want you to be careful of, cognizant of, is that this is our way of telling acids, bases, and salts apart from each other. Okay, so that fifth proficiency, the solubility rules proficiency, that proficiency is basically a multiple choice test. There are 6 possibilities for every single ion, every single compound on that list. It is either soluble in water, soluble salt, an insoluble salt, a strong acid, a weak acid, a strong base, or a weak base. Those are the 6 possibilities on that examination, on that proficiency. And so of those 6 possibilities, you can actually break it down into a 1 out of 2 just by looking at the formula. How do I determine if something is ionic? Well, generally speaking, I'm looking for a metal and a non-metal. Or more precisely, I'm looking for something that is on that polyatomic ions list that we had you memorize. So if it looks ionic, but starts with a hydrogen as the cation, then I know it's an acid. So HCl, hydrogen chloride, hydrochloric acid. HNO3 looks ionic, nitrate's an ion, but starts with hydrogen, that's an acid, nitric acid. Bases, on the other hand, look ionic, start with a metal of some kind, usually, but end with OH. Now, these solubility rules do not apply whatsoever to acids and bases. Acids and bases, we are going to assume are soluble And what we're really trying to seek to find with acids and bases is their strength. And so we'll talk about, and you'll do a post-lecture activity regarding acid and base strength and how to tell them apart. So that's something that you need to kind of look at and look forward to as far as that's concerned. Acids and bases, we evaluate only on strength, not on solubility. These rules are being applied specifically for the solubility of the substances themselves. In terms of, if this substance is ionic, will it dissolve in water? Is it going to fall into the soluble salts category or the insoluble salts category? If it's an acid or a base, we're going to be evaluating it with a different set of rules, a different set of circumstances. So I want you to kind of dissociate yourself from evaluating all of these rules for every compound that exists, because it's not going to work that way. This is really just for ionic compounds that are not acidic, not basic, just salts. So again, here's my list of things that will always dissolve. Now the second list, these are substances that will usually dissolve. And so in the substances that usually dissolve, we have our halide ions, our chlorides, our bromides, our iodides. And for the most part, these are soluble in water. And think about that. Sodium chloride, potassium chloride, magnesium chloride, calcium chloride. Those substances, have been long used by us, and for the most part for their ability to dissolve in water, or at least to, in the case of calcium chloride, to dissolve in water at a lower temperature, which will allow the water to stay liquid instead of freezing and making ice and snow. There are some exceptions that are associated with these. So these are usually soluble. However, if our cation is silver, if our cation is mercury 1, if our cation is lead 2, these three metal ions are the exceptions to the rules. These will make insoluble compounds that will not dissolve in water. So silver chloride does not dissolve in water. Mercury 1 bromide does not dissolve in water. Lead 2 iodide makes a really nice yellow solid that will not dissolve in water. So this is one of the second group. Also in this second group are sulfates. Sulfates are usually soluble in water. In fact, sulfates are used by a number of different transition metals for that reason. We can take copper 2 sulfate, for example, dissolve in water and use that as a source for copper. And that's dissolved in water instead of copper 2 nitrate or others. Sulfates, the exceptions to those fall mainly into two categories. You have in here with our calcium and our strontium and our barium. If you look at your periodic table, the calcium, strontium, and barium, which are not shown up very well here, those are the heaviest of the alkaline earth metals, at least of the ones that are not radioactive. So calcium, strontium, barium, these ones will not dissolve in water. Calcium sulfate, strontium sulfate, barium sulfate, they don't dissolve. What we also have here as well, look, we've got another familiar foe, mercury 1, lead 2. So mercury 1 and lead 2, as far as cations concerned, they don't behave very well. They tend to buck trends quite often. But that's our second tier of solubility rules. So remember, first tier, we have our always solubles. This one, we have our usually solubles. And our last tier, the smallest tier, the one with the most exceptions, are going to be the ones that are usually insoluble. Now, the ones that are usually insoluble, sulfides. Sulfides are usually insoluble. The places where they are soluble, ammonium and alkali metals. Again, this shouldn't surprise you at all, since these were found in rule number 1. So really the only exception here are the alkaline earth metals. So calcium sulfide, beryllium sulfide, magnesium sulfide, those ones tend to dissolve in water. For the hydroxides, same thing. Ammonium hydroxide, alkali metal hydroxides, those are covered by rule number 1. The alkaline earth metal compounds, and even those, solubility on those is tough, but doable. Calcium hydroxide will dissolve in water, but you gotta coax it pretty good to get it to dissolve. Same thing with magnesium hydroxide, same thing with a lot of them. They'll dissolve, but it usually takes some doing to get it to dissolve. It's not gonna be one of those, it's not gonna be like salt water. You know, you take sodium chloride, you mix it in water, and it really doesn't matter what temperature the water is. You stir it long enough, the sodium chloride will go in. And if the water is hot, it goes almost instantaneously. With some of these other ones, you got to really heat it, you got to really stir it up to get it to dissolve, but they do dissolve eventually. These compounds here on this particular list, the carbonates, the phosphates, the oxalates, the chromates, and dichromates, the only exceptions associated with these are your Rule 1 exceptions. Now, one other caveat that we want to put on this, because this is not an exhaustive list. This is not an exhaustive list by any means. There are many, many, many other cations, or many, many, many other anions that are possible for this list. However, just because it's not on one of these lists doesn't mean that it doesn't fall into one of these categories. In fact, what we are telling you is that if you find an ion that is not on one of these lists, unless it's paired with something that is usually something that is always soluble, you can pretty safely assume that it is insoluble. So if you come across a common ion that's not on this list, like iodate or sulfite, you're pretty safe to assume that unless it's paired with sodium or ammonium or something else, acetate, you can pretty safely assume that it's going to be insoluble, and that's going to be in that part of the list that does not dissolve. Any questions about our solubility rules or anything else that we've talked about up until this point?
No.
Okay, so what I would encourage you to do is start looking at that 5th proficiency. Again, it's an auto-graded proficiency, so you should be able to tell how you did pretty much instantaneously. But go ahead and go for those bonus points, and start working your way through that solubility stuff, because the sooner you can understand your solubility rules and understand when things are soluble and insoluble, when things are weak acids and strong acids, the better off you're going to be in terms of handling that last proficiency and the stuff that's coming up in the next couple of days in this chapter 8. So I would start working on that sooner rather than later, not just for the bonus points, but because if you don't have a handle on the solubility rules, when we start talking about net ionic equations and redox, it's going to be really hard for you to catch up and do both at the same time. So the last thing we're going to talk about today, and we alluded to this a little bit in chapter 6 when we were talking about the concept of solution making and the idea of those spheres of hydration. What happens when things do dissolve? And one thing that we should know is that as that solution is forming, as the solute and the solvent are mixing together and starting to come together to make this uniform solution, the solute particles are being separated from each other. The solvent particles are being separated from each other in order to make room for each other in this evenly distributed solution matrix, however you want to put it. But this only occurs, this is where we go back to intermolecular forces. This only occurs if the total amount of intermolecular force for the solution, that is the solute to the solvent attracting each other, is greater than the forces that are holding the solute together by itself or the solvent together by itself. We have to overcome the individual attractions among the molecules and each other in order to get them to attract each other in the solution. And so we have to have better intermolecular forces together than we did separately. And if we don't, then we're not going to see solubility occur. And so all those solubility rules that we just went through, the ones that are insoluble, that's the primary reason why they are insoluble. They are better off separate. They have better forces separately than they do together with the water. And so we talked about this in chapter 6. This is coming back to that idea of spheres of hydration, where the positive ions are being surrounded by the negative poles of the hydrogen bonds in water. And so we see that the positive ions will attract the oxygens. The negative ions will attract the hydrogens because that's where the positive parts of the water molecule are. And as these molecules start to work on that crystal, they'll start to separate those ions from the crystal, and eventually the crystal will cease to exist because all of the ions will have been separated and hydrated by those waters. And so I'm actually gonna stop on this spot here because that really gets us into where we're going to go tomorrow with talking about net ionic equations. But before we completely close it for today, what I'd like to do is take a peek at the post-lecture that we are going to be looking at, the one with the solubility rules associated with it, because that's going to say a lot for us in terms of being able to have some success on the fifth proficiency. So in post-lecture 25, post-lecture 25 is due for the lecture, not today, but actually, it's actually the assignment for 2 days from now, for Thursday morning. So in this, you have the solubility rules. We give you the strong acids and the strong bases. But what I want to point you to is, obviously here are the solubility rules. But what I wanted to point you in the direction of is here. When it comes to acids and bases, the strong acids are these 7 right here: hydrochloric, hydrobromic, hydroiodic, chloric, perchloric, nitric, and sulfuric acid. Those 7. The strong bases are all of your alkali metal hydroxides and your 3 heaviest alkaline earth metal hydroxides, that is calcium, strontium, and barium. Those are your strong bases. Now, again, what we can kind of point to as far as recognition is concerned is the way that we recognize acids is by looking at the formula. The formula says, okay, this looks ionic in terms of I've got a cation and an anion, hydrogen ion plus, chloride ion minus, hydrogen ion plus, chlorate ion minus. But it starts with hydrogen as opposed to a metal. So that's how I can pick out acids. And all of the strong acids look like that. All of the weak acids look like that as well. On the flip side, how do I recognize bases? Well, for the most part, I recognize bases based upon their hydroxides. They look ionic, so they've got a metal, and then they've got a hydroxide as the non-metal or non-metallic anion. So I take a metal hydroxide, it's going to be basic. If it's basic, is it going to be classified as strong or weak? And the strongs are all of your group 1s and your heaviest of group 2s. Your weaks are going to be your light alkaline earth metals, all of your group 3 hydroxides, all of your transition metal hydroxides, and then the one wild card in here is ammonia. Ammonia is kind of odd because we can see it in its molecular form, NH3. We also are known to show it in its ionic form. The ionic form for ammonia, NH4OH, sometimes referred to as aqueous ammonia. And the reason for that is this is NH3 that has been combined with water. So if I take NH3 plus H2O, I would get NH4OH. And from that standpoint, that's how it fits into this model where we've got hydroxides as our bases and how we determine our bases. Now, there is one other thing to mention with regards to acids and bases. And as far as proficiency 5, the solubility rules proficiency is concerned, that manner of identifying acids and bases, hydrogen ions for the acids, hydroxide ions for the bases, that works pretty well. There is one other way of determining acid and base behavior, and it's something called Bronsted-Lowry theory. Bronsted-Lowry theory states that anything that gives up a hydrogen ion is an acid, and anything that gives up accepts a hydrogen ion is a base. And so that does kind of muddy things a little bit, but what it really does for us in terms of reactivity is it allows us to show acid-base behavior for things that don't fall into this very strict kind of characterization of hydrogen ion or hydroxide ion.